Ladies and gentlemen, today, I have the privilege of delving deeper into one of the most awe-inspiring and cutting-edge fields of human endeavor, the engineering behind spaceships. The exploration of outer space, with its limitless expanse and the promise of discovering new frontiers, has always captured our imaginations. However, it is the tireless efforts of engineers that transform these dreams into a tangible reality. As we venture further into the cosmos, the role of engineering in space travel becomes increasingly critical, and it's important to appreciate the multifaceted components of this endeavor. One of the fundamental challenges that engineers face in spaceship design is achieving the delicate balance between structural integrity and weight reduction. The spacecraft must withstand the colossal forces experienced during launch, yet it must also be as lightweight as possible to conserve fuel and facilitate a successful journey. Advanced materials such as carbon fiber composites, with their exceptional strength-to-weight ratios, are harnessed to build spacecraft that are both robust and lightweight, enabling them to endure rigors of space travel. In the quest to reach distant celestial bodies, propulsion systems stand as the workhorses of space exploration. Traditional chemical rockets are a marvel of engineering, but engineers are constantly pushing the envelope. Ion propulsion, for example, relies on the acceleration of charged particles to achieve higher speeds and greater efficiency, allowing for extended missions and resource conservation. In contrast, the concept of nuclear propulsion, while challenging due to safety and environmental concerns, holds the potential to revolutionize space travel by providing substantial thrust for faster, more ambitious missions. Spaceship engineering also places a premium on life support systems, as the vacuum of space, extreme temperatures, and cosmic radiation pose grave threats to astronauts. Engineers are tasked with creating self-contained ecosystems that ensure the health and well-being of the crew. This includes the development of advanced life support technologies that recycle air and water, minimizing the need for resupply from Earth. Furthermore, the choice of radiation shielding materials and the design of habitat structures are critical engineering considerations in protecting astronauts from the harsh space environment. Another essential element in spaceship engineering is navigation and guidance systems. The precision required to reach distant celestial bodies, rendezvous with space stations, or explore other planets is staggering. Engineers have developed intricate computer systems, star trackers, and gyroscopes to ensure a spacecraft's precise positioning and the capability to make course corrections, often guided by autonomous algorithms to overcome communication delays and enable real-time decision-making. As we explore the cosmos, communication systems are another engineering marvel. Deep space missions depend on complex networks of antennas and satellites to transmit data over vast distances. Engineers must contend with signal degradation, interference from cosmic phenomena, and communication delays that can stretch to minutes or even hours, all of which require the development of advanced signal processing techniques and highly efficient data compression methods. The challenge of power generation is also paramount in spaceship engineering. Engineers have devised innovative solutions, such as solar panels and radioisotope thermoelectric generators, RTGs, which convert the heat from decaying isotopes into electricity. However, they are constantly seeking more sustainable and efficient methods, including research into nuclear fusion as a future power source for spacecraft, which could revolutionize our ability to generate energy during long-duration missions. Spaceship engineering represents the pinnacle of human ingenuity and interdisciplinary collaboration. It is a field where innovation and precision combine to overcome the formidable challenges of space travel. From the early moon landings to the robotic missions exploring distant planets and the audacious plans for human missions to Mars, spaceship engineering has propelled humanity into the cosmos, expanding our understanding of the universe. As we gaze towards the future, with dreams of interplanetary colonization and deeper space exploration, we can remain confident that engineers will continue to push the boundaries, turning the once fantastical dreams of space travel into tangible achievements. Spaceships are more than just vessels, they are feats of engineering brilliance requiring immense precision and innovation across numerous complex systems working in unison. The structural design of a spacecraft alone is a massive undertaking, as the frame must withstand the deafening acoustic waves and violent vibrations of launch, while also maintaining integrity in the harsh vacuum of space across a wide temperature range. Engineers select materials like aluminium alloys and composites for their strength and lightweight, while advanced welding and joining techniques ensure robust connections between components. But the structure is only the beginning. The propulsion systems, such as powerful liquid fuel rockets or high-efficiency ion engines, must generate enough thrust to first break free of Earth's gravity and then accurately steer across millions of miles. Power systems, including radioisotope thermoelectric generators with heat-resistant materials or large solar panel arrays, are capable of producing consistent electricity for decades under intense radiation. The life support systems continuously monitor and regulate oxygen levels, carbon dioxide removal, water recycling, waste management, fire detection, and temperature within the living habitats and across the spacecraft. Guidance, navigation, and control systems process sensor data and run optimized algorithms to autonomously direct the spacecraft's orientation, trajectory, and speed. Robotic arms and rovers further expand the capability for external satellite servicing, repair, debris removal, and more. Communication systems enable vast amounts of data transfer across astronomical distances back to Earth using high-gain antennas and specialized protocols. Every single subsystem on board a spacecraft represents the absolute cutting edge of human engineering capability. In this speech, we will explore the fascinating intricacies and innovations within the field of spacecraft engineering that allow us to push the boundaries of our knowledge by launching machines and humans beyond the constraints of Earth. The propulsion systems of spaceships are the lifeline of space exploration, propelling these vessels through the vast cosmic void. While traditional chemical rockets, like those used in the Apollo missions, have been incredibly successful, engineers are constantly seeking ways to enhance their efficiency and develop alternative technologies. One of the most promising advancements in space propulsion is ion propulsion. Ion propulsion systems work on a different principle than traditional chemical rockets. Instead of expelling large amounts of propellant at high speeds, ion engines use a much smaller amount of propellant and accelerate it to extremely high velocities. This process is achieved by using electric or magnetic fields to ionize the propellant, typically xenon gas, and then expel these ions at high speeds. The engineering behind ion propulsion involves creating efficient ionization and acceleration systems, as well as designing power sources, often in the form of solar panels or nuclear reactors, to provide the necessary electrical energy for sustained propulsion. Ion engines are known for their fuel efficiency, which allows for longer missions and greater payloads. They have been employed in various spacecraft, including the Dawn mission to the asteroid belt and the propulsion system used on the Starlink satellite constellation. Nuclear propulsion is another revolutionary concept that engineers are actively exploring. Nuclear thermal propulsion and nuclear electric propulsion are two primary branches of nuclear propulsion. Nuclear thermal propulsion involves using a nuclear reactor to heat a propellant, like hydrogen, to high temperatures, and then expelling it to produce thrust. The challenge for engineers is to design compact, reliable nuclear reactors capable of withstanding the harsh conditions of space. Nuclear electric propulsion, on the other hand, uses nuclear reactors to generate electricity for ion propulsion systems, combining the efficiency of ion engines with the power of nuclear technology. The development of safe and efficient nuclear propulsion systems remains a significant engineering endeavor, but they hold the potential to revolutionize deep space missions. reducing travel times and enabling human exploration of distant planets like Mars. Additionally, engineers working on propulsion systems must consider the specific requirements of each mission. Factors such as the payload mass, destination, duration of the mission, and available resources all influence the choice of propulsion technology. The engineering challenges extend beyond the propulsion systems themselves, encompassing the spacecraft's structural integrity, heat management, and power generation systems, as they need to support and be integrated with the chosen propulsion technology. The propulsion systems of spaceships are not only the backbone of space exploration but also a constant frontier for engineering innovation. The quest for greater efficiency, reduced travel times, and expanded mission capabilities drives engineers to explore alternative technologies like ion propulsion and nuclear propulsion, ultimately expanding the horizons of human space exploration, ensuring the survival and well-being of astronauts in the harsh environment of space is one of the greatest challenges for spaceship engineers. The vacuous void offers no breathable air, no atmospheric pressure, and no protection from the sun's intense radiation and extreme temperature swings. Every aspect of the spacecraft must be meticulously designed to sustain human life. Sophisticated life support systems continuously monitor and regulate oxygen and carbon dioxide levels, humidity, contaminants, and air circulation inside pressurized habitats and spacesuits. These systems often employ molecular sieves, scrubbers, and electrolysis processes to filter impurities and regenerate breathable air while minimizing power consumption. Water recovery systems utilize vapor compression, distillation, and chemical treatment to recycle moisture from wastes, urine, and humidity condensate back into potable drinking water. Waste management tracks, collects, and stabilizes human metabolic waste. Fire detection and suppression systems quickly identify fires before they deplete oxygen supplies. Heating and cooling loops precisely control air temperature and humidity. These integrated life support systems enable astronauts to live and work in space for months without any outside resupply. In addition to air, water, and temperature regulation, engineers must protect astronauts from radiation. Aluminium hulls and polyethylene sheeting provide shielding from solar particles. Equipment is strategically placed and water supplies positioned to create safe havens during solar storms. Radiation sensors constantly monitor exposure levels. New lightweight shielding materials are being developed to better block cosmic rays and other ionizing radiation. With human lives at stake, radiation protection is an absolute necessity in spaceship design. By innovating multifunctional, closed-loop life support systems and radiation shielding, spaceship engineers enable incredible journeys far beyond Earth. Their tireless work translates advanced technologies into practical solutions that protect fragile human bodies across millions of miles. Pushing the boundaries of sustaining life where none should exist demands brilliance and dedication from these exceptional engineers. The monumental challenge of keeping astronauts alive and well drives cutting-edge developments that may someday benefit human habitats on Earth and beyond. One of the fundamental engineering challenges in spacecraft design is achieving the delicate equilibrium between minimizing weight and ensuring structural integrity. The spacecraft's structure needs to be lightweight to reduce the cost of launching it into space. However, it must also be strong enough to endure intense forces and vibrations during the launch phase. To address this, engineers often employ advanced materials and innovative structural designs. Firstly, carbon composites have revolutionized spacecraft construction. These materials consist of carbon fibers embedded in a resin matrix, providing an exceptional strength-to-weight ratio. By incorporating carbon composites into the spacecraft's structure, engineers can significantly reduce its mass while maintaining structural integrity. This is crucial for minimizing launch costs, as less propellant is required to carry a lighter spacecraft into orbit. Additionally, Advanced alloys play a critical role in spacecraft engineering. These alloys are tailored to provide exceptional resistance to the extreme temperature fluctuations and radiation exposure of space. They are used in various components, including the spacecraft's hull, heat shields, and propulsion systems. The choice of alloys is driven by the need for both durability and weight reduction. Furthermore, engineers often employ innovative design concepts to enhance the spacecraft's adaptability to the ever-changing conditions of space. This involves developing modular and flexible architectures that allow for component upgrades or replacements during long missions. For example, modular payload bays or standardized connection interfaces make it easier to integrate new instruments or technology as missions progress. In terms of robustness, spacecraft must be designed to withstand the challenges of space, including micrometeoroid impacts, extreme temperatures, and the vacuum of space. Engineers incorporate protective shielding, such as multi-layer insulation and micrometeoroid shields, to safeguard the spacecraft and its delicate instruments from potential damage. A vital consideration in spacecraft design is thermal control. In the vacuum of space, there is no air to conduct heat away from the spacecraft, so engineers must employ intricate systems involving radiators and thermal blankets to manage temperature extremes. Additionally, the adaptability of a spacecraft involves systems that can self-correct or adapt to unforeseen circumstances. Advanced algorithms, redundancy in critical systems, and autonomous navigation capabilities are all essential engineering components to ensure the spacecraft can respond to unexpected challenges during its mission. The design and construction of spacecraft involve a complex interplay of engineering elements that strive to create a lightweight, robust, and adaptable vessel for space exploration. Materials like carbon composites and advanced alloys, innovative structural designs, and systems for thermal control and adaptability are all integral to the success of these remarkable engineering achievements in the realm of space travel. This meticulous engineering work empowers us to venture further into the cosmos and accomplish groundbreaking missions in the name of science and human exploration. Navigation and guidance systems represent some of the most sophisticated engineering in spacecraft design. The level of accuracy required to travel millions of miles and rendezvous with space stations, landers, or orbiting moons is mind-boggling. Even the slightest computation or maneuvering error could lead to complete mission failure. Engineers equip spacecraft with advanced inertial measurement units containing precision laser gyroscopes and accelerometers that continuously track orientation, rotation, and velocity. Star trackers image constellations and calculate position relative to fixed points in space. Sun sensors and Earth horizon sensors add supplementary positional data for calibration. Laser altimeters, lidar, and other proximity sensors guide delicate maneuvers, docking procedures, and landings. Powerful onboard computers run complex astrodynamic calculations, orbital mechanics algorithms, and autonomous navigation software to process sensor data. They plan trajectories, correct courses, and execute thruster firings with incredible speed and accuracy. For human-rated vehicles, engineers implement redundant systems and backup computers to maximize reliability and safety. Deep space communications allow ground controllers to uplink additional navigational fixes and course corrections. But due to long delays, spacecraft must often navigate independently for minutes, hours, or even days at a time. Engineers thus program spacecraft with artificial intelligence and machine learning to make automated decisions using contextual sensor data. The brilliant guidance and navigation designs allow spacecraft to traverse tremendous distances, hitting targets smaller than a basketball court after journeys of over 100 million miles. They enable delicate orbital insertion maneuvers and precise landings on airless, alien worlds. The navigation expertise of spacecraft engineers makes space travel possible. Their relentless innovation continues to advance this vital capability even further. Communication systems are an equally vital component of spacecraft engineering, enabling deep space missions to transmit signals across truly vast distances. Engineers must build intricate networks of antennas, ground stations, and relay satellites to maintain a stable link between the spacecraft and mission control. This becomes exponentially more difficult the farther a probe travels from Earth. The first challenge is combating signal degradation. Radio waves become dispersed and attenuated over long distances. Large, high-gain directional antennas focus signals into concentrated beams aimed directly at Earth. Boosting transmission power improves the signal-to-noise ratio. Error-correcting codes help extract the original message from weak or corrupted signals. Next, engineers have to account for cosmic noise and interference. The sun emits charged particles that can distort or jam radio signals. The atmosphere diffracts signals, scattering energy away from the intended receiving antennas. Even stars and dust clouds generate electromagnetic noise. Spacecraft use shielded electronics and selectively choose transmission windows when space weather is calmest. Finally, communicating across such immense separations incurs long delays. For a Mars mission, it takes 4 to 24 minutes for signals to traverse the distance, making normal conversations impossible. Engineers optimize data compression, create highly autonomous systems, design smart antennas that point while transmitting, and prioritize critical data so nothing essential is lost. By innovating clever communication systems, engineers enable deep space explorers to phone home despite operating over 250 million miles away. Their technical brilliance allows a rover on Mars to send back high-resolution images and scientific data as if it were just around the corner instead of an average of 140 million miles away at the speed of light. Spacecraft communication systems represent some of the most advanced telecommunications technologies ever engineered by human hands. Spaceships operate in an environment where traditional power sources are often inadequate or impractical. As we mentioned, two common methods of power generation are solar panels and radioisotope thermoelectric generators, RTGs. Solar panels have been the go-to choice for many spacecraft. They convert sunlight into electricity using photovoltaic cells. While solar panels are reliable and proven, they have limitations. The farther a spacecraft travels from the sun, the less energy it can harness from solar radiation. Engineers face the challenge of maximizing the efficiency of solar panels by developing advanced, lightweight, and high-efficiency photovoltaic cells. This involves materials science, as engineers must design panels that can endure harsh conditions like extreme temperatures and radiation exposure while still generating sufficient power. Radioisotope thermoelectric generators, on the other hand, offer a different solution. They use the heat generated by the natural radioactive decay of isotopes to produce electricity. RTGs are extremely reliable and can function for extended periods, making them ideal for deep space missions. However, their use requires careful engineering to ensure the safety of both the spacecraft and the environment. Engineers work to minimize the environmental impact and radiation hazards, requiring stringent containment measures. Beyond these established methods, engineers are exploring more advanced and sustainable solutions, such as nuclear fusion. Fusion power is the process that fuels stars, combining light elements to release vast amounts of energy. If harnessed successfully, fusion could provide an almost limitless and highly efficient source of power. However, achieving controlled nuclear fusion on Earth remains a significant engineering challenge. Scientists and engineers are working on projects like ITER, the International Thermonuclear Experimental Reactor, To crack the fusion code, the construction and operation of these fusion reactors require sophisticated materials engineering to withstand the intense heat and pressure generated during fusion reactions. Another innovative approach is the use of advanced energy storage systems. Lithium-ion batteries have improved the efficiency of power usage and storage on space missions. Engineers are continually researching new battery technologies, including solid-state batteries and supercapacitors, to enhance the power storage capabilities of spacecraft. These technologies reduce the reliance on immediate power generation and allow for more efficient power distribution throughout the mission. Spaceship engineering faces a multifaceted challenge in power generation. Engineers must balance energy efficiency, sustainability, and reliability in an environment where traditional power sources may not suffice. As we look to the future of space exploration and the ambitious missions to the Moon, Mars, and beyond, the development of innovative power generation solutions will be a critical aspect of enabling these missions to thrive. This demonstrates the engineering community's unwavering dedication to pushing the boundaries of what's possible in the realm of space travel. Finally, the ever-present factor of resource efficiency cannot be overlooked. Every kilogram of payload sent into space is costly, so engineers are constantly searching for ways to make spaceships lighter, which in turn reduces the cost of launches. Space exploration represents the pinnacle of human engineering capability, only made possible through the collaborative brilliance of multidisciplinary experts. The monumental achievements that have propelled humankind into the cosmos stand as enduring testaments to determined innovation. The crowning accomplishment of 20th-century space travel, the Apollo moon landings, exemplified the incredible potential when engineers, scientists, and technicians pool their knowledge. Thousands of individuals work tirelessly to surmount the countless technical obstacles and manifest the dream of setting foot on another world. From the mighty Saturn V rocket to the compact Apollo command modules, every system and component was engineered to unprecedented extremes. In the decades since, space agencies have dispatched probes across our solar system to explore alien worlds. Orbital mechanics experts plotted complex gravity-assisted trajectories to deliver spacecraft like Voyagers 1 and 2 into interstellar space. Materials engineers developed heat shields to protect spacecraft during atmospheric entry on planets and moons. The Spirit and Opportunity Mars rovers demonstrated advanced autonomous navigation to travel dozens of kilometers across the Martian surface. Jupiter's moon Europa may soon be explored for signs of life beneath its icy crust, thanks to cutting-edge deep space vehicle design. Looking ahead, we now prepare for the next era of human deep space exploration with Mission to Mars. This monumental undertaking will require immense innovations in in-situ resource utilization, long-duration life support systems, durable space habitats, sustainable food production, and much more. The knowledge gained from this difficult but essential expedition will expand humanity's understanding of our universe exponentially. The awe-inspiring accomplishments of space travel stand as tributes to the human spirit of exploration and the engineers who defy the bounds of what is believed possible. Continued collaboration will propel the ambitious vistas only imagined today into tomorrow's remarkable realities. In conclusion, spaceship engineering represents the pinnacle of human ingenuity. It is a field where innovation and precision intersect to overcome the daunting challenges of space travel. Engineers are at the forefront of creating solutions to these challenges, and their work encompasses a vast array of intricate components and systems. When we think about interplanetary colonization, for instance, we must consider the complexities of life support systems. Engineers are developing advanced recycling technologies that allow astronauts to reuse water and regenerate oxygen, reducing the need for constant resupply from Earth. They are also designing closed-loop ecological systems that mimic the Earth's natural processes, enabling long-term sustainability on other planets. Exploration of the cosmos introduces unique engineering hurdles such as radiation shielding, Space engineers are researching and developing novel materials and shielding strategies to protect astronauts from the harmful effects of cosmic radiation during long-duration missions. Cutting-edge research is exploring materials with self-healing properties that can automatically repair themselves in the harsh conditions of space. Another aspect of spaceship engineering in our future ambitions is the development of highly autonomous robotic systems. These systems are crucial for tasks like resource extraction on the Moon or Mars, where astronauts cannot be present at all times. Engineers are designing sophisticated robots that can perform complex operations, adapt to unpredictable environments, and communicate with mission control on Earth over vast distances. As we venture further into space, power generation becomes a critical concern. Engineers are pioneering advanced energy sources, including compact nuclear reactors, which can provide a reliable source of energy for habitats and equipment in space, reducing reliance on solar panels and ensuring energy independence on distant celestial bodies. Furthermore, engineers are exploring regenerative life support systems that can turn waste products into valuable resources. This innovation not only makes missions more sustainable but also reduces the need to send massive amounts of supplies from Earth, cutting costs and environmental impact. In the quest for exploring other planets, precision engineering plays a significant role in the design of landing systems. Landing on distant worlds is a delicate and complex task that requires pinpoint accuracy. Engineers are developing landing systems that use autonomous navigation, terrain analysis, and sophisticated guidance systems to ensure a safe and controlled descent onto alien landscapes. The dreams of interplanetary colonization and the exploration of the cosmos are not merely fantasies, they are pursuits driven by the dedication and ingenuity of engineers. These experts continually push the boundaries of what is possible, creating the foundation for our future among the stars. Through their tireless efforts and unwavering commitment to solving the intricate engineering challenges posed by space travel, engineers are expanding our horizons in ways that are truly out of this world. Thank you.